going back to a different type of edge, edges within the image. If we look here, we have an image, we have an area of reasonably high data, of higher data, and an area of slightly lower data. Similarly, slightly lower, slightly higher here. And all of these are of this higher character, and then there's suddenly jump down to the slightly lower character. There's an edge here, illustrated with this black line. There's also an edge with this grey line, but we're not going to investigate that right now. We're going to look at trying to find this edge, which we could see, but how does that exist for the computer? Well, we can use, in this example, we're going along here, along the x-axis, so we can use the Sobel X. Sobel is an edge detection filter. There are many different filters for this job, but we'll just examine the Sobel, and it looks like this. So we're going to apply this window, we're going to move it over the image again, as we did before with calculating the mean, but this works slightly differently in that when we put our kernel there, we're going to calculate a new value for this cell here, which is that one there, and we can see the result is going to be -3, but how do we get to that? Well, we take -1 times 21, so that's -1 times 21, 0 times 22, 1 times 21. Sum those up, it actually comes to 0. We go down to the next row here, -2 times 22, 0 times 22, 2 times 21. That sums up to -2. The next row down, -1 times 23, 0 times 22, 1 times 21. That sums to -1. We then sum all of those up and we get -3. That's that number there. We get closer to the edge. Now we're standing at this edge here. Here we were far away from the edge. Now we're actually standing at the edge. We've got part of our kernel is sticking out into this other area. It's overlapping into this lower area. So there must be something happening here. So when we redo that calculation, we can see that using the same Sobel X filter here, on the values here, -1 times 21 and the -2 times 21, here, we can see that we do the same calculation, the sum then becomes -40, so the absolute value is much larger. Here we had a 3, here we have a much larger absolute value. They're both negative in this case, but that's not important, it's the absolute value that we're looking at. And that tells us that there is an edge here, or there's a tendency towards an edge. So that's how edge detection can work using, for example, a Sobel filter. We need to move this, rotate the filter around to detect the changes in the y direction. That we call the Sobel Y. But that's perfectly doable. It's a simple enough operation. And then if we want to get the detect lines in any direction, we can actually combine these using Pythagoras, and we calculate using Pythagoras here the size of that change in the direction, and we can get the angle using trigonometry, the angle of that change of the lines, using the combination of the change in x and the change in y. Related to that last point, we have distance through a raster. This seems like a trivial point perhaps, but we can calculate distance in two different ways. We have perhaps the more standard way using Pythagoras, where we have x squared plus y squared and the root of the sum of those two to get the distance. And that we can see, so from this central pixel, the distance out is, we've got the y squared there, and we've got the x squared there, and then that gives us a distance of 2.8 to that edge there. So 1.414 you should remember as a number is the hypotenuse of a unit triangle. So we can see that the distance out to that corner there is 2.8 in this example. But we can also calculate distance in the Manhattan fashion, named so because of the regular grid of streets in Manhattan. So we can't go directly up there, we go along and then up, and that's our distance 4. So we go along 2, and then up another one, and then up one more to get to 4. So we can't go diagonally over, we can only follow these cardinal directions. That gives us the Manhattan distance. This concept of only being able to go along the right angles or to be able to use the diagonals also comes into another form of analysis where we do that thing that I've said previously we can't do. Yes, what we do is we try and group pixels together. We tell them about their neighbors. We allow them to become objects in a sense. We can group them together. We can do this in two ways. One grouping, illustrated in the upper example, we only look at the neighbors that are left and right of us or up and down. We don't look at the diagonals. So here we have a pixel value of 1, a pixel value of 1, a pixel value of 3, so on. And we can see that these would belong together. They're both 1s. These are all 2s. Here we have a 4, and here we have some 3s, and there's a 3 down there as well. So when we group these together, we can perform an analysis that says, well, that one is, if I start here, that's not a 2, that's not a 1, that is a 1, okay, we belong together. That's not a 1, that's not a 1, okay, end. So we're group 1. Then we go to the next step. Well, I'm a 3. That's a 3 down there. That's a 3 over there, okay. So all of these 3 belong together. And then we go and look here. Well, that's a 2, that's a 2. Okay, we belong together. That's a 2, that isn't a 2, okay. We can go down here and look. Oh, that's a 2, that's a 2. Yeah, you get the idea. We're checking where we have neighbors that are the same as us. But that then means that this 3 isn't part of that group. Because we don't see it from here, we don't get that diagonal. But if we want to, we can say to this algorithm, well, check the diagonals as well. So for most of this analysis in this simple example here, it's not going to make any difference. But for this group here, when we are analyzing this, it's not just checking up and down, left and right, it's also checking over that diagonal. It says, oh, that's one of us. So that pixel then becomes included in this group. So that is now part of this second group, rather than being its own group on its own as it was up here. So this is how we can group raster cells together. Different algorithm, or it's a very similar algorithm, but we can extend it so that it looks at the diagonals if we want. That is going to be a choice that we have to make based on other information that we have about the data.